Today we're going to take a look at a really important law called Hess's Law. The cool thing about this is we're actually in Mrs. Hess's old classroom. Before she retired, she used to teach in this room. I used to be down the hallway, but now, kind of with Science Fair, the Science Fair project room, I've moved up to this room. Not that she has anything to do with Hess's Law, just like I don't have anything to do with the Balmer series and spectroscopy, but it's a cool little coincidence. So what we're going to do is we're going to take a look at delta H values for reactions where it might be hard to measure delta H. But if we can look at delta H values for reactions that we can easily figure out, maybe with calorimetry, just like we took a look at the last section, if we can kind of somehow combine those reactions that we know with their known delta H values, combine them in a certain way so that we can still get the reaction that we're hoping for, that would allow us to calculate the delta H values. So last section, calorimetry, was all about measuring delta H values for reactions, whereas now we're going to use those values from tables and textbooks, and we're going to calculate delta H values for new reactions. So the key behind Hess's law is that if a reaction could be carried out in multiple steps, the overall reaction is equal to the sum of the enthalpy changes for the individual steps. And the whole reason for this, even though state functions and path functions might be beyond the scope of the AP exam, I like to introduce that because delta H is a state function. It doesn't matter if we go from this top reaction down to this reaction in one step, or if we do it in two steps. Either way, we're going to get the same delta H value. Same thing over here. We could do it in one step, or we could do it in two different steps, two different pathways. There's actually, I think, 3 different pathways up here. One step versus this little combined step versus this different combined step. The pathways are different, but because delta H is a state function, we end up getting the same answer, negative 890 kilojoules. So let's take a look at Go Figure 5.21. What process corresponds to the negative? I got cut off a little bit. Negative, maybe an option negative. I'll just add an extra space there. What process corresponds to the negative 88 kilojoules of enthalpy change? Think about that and then go ahead and respond. All right, hopefully you realize that this little step here, CO2 is a gas, H2O is still 2H2O. The only difference is that we have a gas going to a liquid. Well, gases have higher energy, liquids have less energy, so this loss of energy corresponds to condensing 2 moles of water vapor to 2 moles of liquid water. Let's take a look at page 184. They give it some thought. What effect do these changes have on delta H for a reaction? If we reverse the reaction, how would that affect things? And if you multiplied the coefficient of the equation for the reaction by 2, how would that affect things? Think about that and go ahead and respond. All right, so reversing the reaction, hopefully you figured out that the delta H would have the same number, the same magnitude, but it would be the opposite sign. So if it was negative 890 kilojoules the first way, the reverse reaction would have a positive 890 kilojoules. If you double the reaction, the delta H would be doubled as well, and that's because delta H, as long as it's not in a molar ratio or per gram ratio, delta H for a reaction would be an extensive property. The amount of heat corresponds to how much reactants and products there are. All right, let's take a look at Go Figure 5.22. Suppose the overall reaction were modified to produce 2 moles of gas rather than the 2 moles of liquid water vapor here. would any of the delta H values change? Think about that and go ahead and respond. All right, so hopefully you realized that this is very similar to that previous graph. Liquid has less energy, so the gas would end somewhere up here. And if you remember from that previous slide, go back a couple slides, the gas has 88 kilojoules more energy. So yeah, that's definitely going to change the overall process here. So in going from here to here, this H2O gas would have an additional 88 kilojoules, so that would make that negative 519 kilojoules. Same thing down here. We're ending with liquid water, but if this would get shifted up by that 88 kilojoules, this would end up being negative 802 rather than the negative 890. All right, so let's go ahead and take a look at a sample exercise here. The enthalpy reaction for the combustion of carbon to carbon dioxide, this one right here, is negative 393.5 kilojoules. And the enthalpy for the combustion of carbon monoxide to carbon dioxide is negative 283.0 kilojoules. So now the question is, well, what happens if I don't want to go from carbon to carbon dioxide, but I simply want to go from carbon to carbon monoxide? So we're looking at this third equation here, and we're going to use those two known equations to figure out what we want. So the way I like to solve these problems, go ahead and give my cheesy pen smile. Cheese. All right, there we go. So I like to go ahead, kind of like a net ionic equation, I like to figure out where I want to be at the end. So at the end, I better end with carbon solid. So it's really important to know the states of matter, because all known quantities and their states have to be identical. Plus 1/2 of O2 in the gas phase turns into carbon monoxide in the gas phase. And again, we want to know what this delta H is. So now it's just like a puzzle piece. Because I have carbon on the left-hand side, I'm going to use this first equation as written, because there's one carbon solid in that reaction, and I want one carbon solid in the final reaction. So carbon solid plus O2 gas is turning into carbon dioxide gas, and that gives off 393.5 kilojoules. So that's why it's negative. Now, so I simply compare what I want. This is what I want. This is what I have. So that's a good sign. Somehow I'm going to have to cancel out one of these oxygens, or half of those oxygens, and I'm going to have to get rid of this carbon dioxide. Well, you can see in this second reaction here, I do have carbon dioxide, but that would make more of it. So what we're going to do is we're going to flip that reaction. So I'm going to put the carbon dioxide gas on the left, and rather than making the carbon dioxide, we're going to split that into carbon monoxide gas and half of an oxygen gas molecule. And when we flip a reaction, we'll get the same delta H. It would just be the opposite sign. So rather than being a negative 283, it would be a positive 283 kilojoules. So then we just want to go through and strike out everything that cancels. So carbon dioxide gas cancels. This half of an oxygen molecule would cancel out 1/2 of those oxygen molecules, and we're left with carbon solid, oxygen gas producing carbon monoxide, and that's exactly what we want down here in this final reaction. So now Hess's law tells us that we can simply add these two reactions together. So negative 400 plus 283, I don't know, that's going to be about 100, yeah, maybe 110. So let's grab a calculator and see what we get here. So negative 393.5 plus 283. They both have one decimal place, so I get to keep one decimal place. Negative 110.5. Yeah, I probably could have figured that out without a calculator. Oh, okay. So negative 110.5 kilojoules. And let's see, double check, did we actually solve for what we wanted? Yeah, now you might be wondering why are these in kilojoules here, but whereas this is in kilojoules per mole, well, that's per mole of carbon. Well, this reaction has 1 mole of carbon, so that's negative 393.5 kilojoules for this reaction. Now, for some reason, this would say 2 carbons. Because this is per mole of carbon, we'd have to double that. But yeah, everything's per mole, and we have 1 mole of the carbon monoxide. We have 1 mole of the carbon. So yeah, we're good to go here. Take a look at the answer key. Sure enough, negative 110.5 kilojoules. All right, let's take a look at another sample exercise, 5.9. And you'll notice that there's like a little play button up here. Anytime you see that play button, that means on the online textbook they would have kind of a solved problem with a professor showing that example. So again, it does a nice job in the textbook going through how to solve the problem. I'm going to solve the problem here, but if you just want to hear somebody else explain it, that's what that little play sign means. So in this problem, we are trying to calculate 2 carbon solids plus hydrogen forming, this would be ethene. So a carbon double bonded to a carbon. Oh no, that would actually be acetylene. So that has to be a triple bond, 1H on this side, 1H on that side. So that would be acetylene. We oftentimes use that in welding. Oh, I forgot my cheesy pen face. Cheese. All right, there we go. So let's figure out what we have to do to these reactions. Because I need 2 carbons on the left, I'm going to go back and double this reaction, which means I need to double this reaction. I need a hydrogen gas, which this reaction has a hydrogen gas forming water, so I'm going to use one of those. You'll notice I need that acetylene on the right-hand side. So I'm just going to write this down here in the reverse order. So I'm going to flip it. So I have 2 carbon dioxides plus, and that's the gas phase, plus water, which is the liquid phase, and that is turning into acetylene, which is a gas, and 5 halves of an oxygen molecule. You'll notice that in thermochemistry and electrochemistry, it's pretty common to have fractional coefficients. And the reason for that is we have certain delta H values that we figure out, that we know from certain equations. And because we usually want it for, let's say, 1 mole of acetylene, we wouldn't want to go back and double that reaction and have it for 2 moles of acetylene. So in the textbook, you would see that this reaction is negative 1299.6 kilojoules per mole of acetylene. So that's why we write it that way. And when we flip that, so we are going to want to flip that. So we would get 1299.6 kilojoules. Now is kind of the fun part, just making sure everything cancels out. So we have 2 CO2 gases there, 2 CO2 gases there. We have half of an oxygen molecule here, but we have 2 oxygen molecules there. So 2 would be 4 halves plus another half would be 5 halves of an oxygen molecule, 5 halves of an oxygen molecule. Water is a product, water is a reactant, and I believe this reaction is all set to go. So we have our 2 carbons, we have our hydrogen gas, everything canceled out, and we produced our acetylene. So now we simply have to add these together. So negative 400 times 2 is about negative 800. Negative 800 plus another 200 would be negative 1,085. We'll just say negative 1,100. Negative 1,100 plus 1,300. I'm thinking the answer is around 200 kilojoules. So let me grab a calculator, do the final math. Everything's got one decimal place, so we'll just add everything up to one decimal place. So positive 1299.6 minus 285.8 minus 393.5 times 2. And I get 226.8 kilojoules. So the overall reaction is 226.8 kilojoules, and that would be endothermic. It's going to take a lot of energy to go into these because carbon and hydrogen are fairly stable. To produce something like acetylene, it's going to take energy to do that. And let's just go ahead and check the answer key, make sure we did that all correctly. Negative 226.8 kilojoules. Perfect. All right, and with that, that wraps up chapter 5.6. And you can see here we're going to be getting ready for our own calorimetry experiment. We're going to be designing a hand warmer lab, looking at the enthalpy of forming solutions, various salts in water. And then eventually what we're going to work on is chapter 5.7, which would be the enthalpy of formation. So that's a very specific type of reaction, a formation reaction, and we're going to figure out what the enthalpies of formation are for those reactions. All right, have a great day, folks.